Okay, today we're going to continue on with some molecular geometry using VSEPR model. Yesterday we saw how we treat the electron clouds as balloons, and you count how many groupings of electrons around the center atom. A grouping is a lone pair, a single bond, a double bond, or a triple bond. We call them all pairs, even though it's a triple bond and not truly two electrons. If you have two pairs, they get as far apart as they can, and that's making a linear molecule, 180-degree angle between the bonds. Between the electron pairs, I should say. If you have three pairs, three groupings, they're going to form a flat triangle, or to speak more scientifically, I guess, trigonal planar shape. So the electron pairs, as your central atom, will be 120 degrees apart from each other. If you have four pairs, you get a tetrahedron shape, or a tetrahedral molecule. Central atom in the middle. All the pairs point to the corners of a tetrahedron. And so it turns out the bond angle inside a tetrahedron is 109.5 degrees, which, by the way, is very similar to water's bond angle, so that gives you some ideas there. We're on the right track. Trigonal bipyramidal, if you have five pairs. Now notice, here we're getting into expanded octets, aren't we? You'd think most atoms are going to have four pairs, tetrahedral geometry, because that's what we want, 8 electrons. But don't forget, if you have double bonds, you can get three groupings. Maybe this one over here is a double bond, and you still have 8 electrons, but they're only grouped in three groupings. So trigonal planar can happen with double bonds. It can also happen with incomplete octets, similar to linear. If you have, like carbon dioxide we looked at yesterday, a double bond and another double bond, that's just two groupings, ends up being linear. So with double or triple bonds, you can end up with linear shapes. Or you could also, obviously, with an incomplete octet, end up that way. With trigonal bipyramidal, 5 pairs, it's got to be an expanded octet. So these are pretty rare to see, but they do happen. And for sample problems, we throw some at you because that's what we do. Notice the unusual thing here with trigonal bipyramidal. Maybe it's easier to see down here. The bond angles are not all equivalent. Okay? With trigonal planar, sorry about that. With trigonal planar, every bond is 120 degrees from all the other. It's symmetric. No matter how you turn it, it looks the same. Same with the tetrahedral shape. It's all 109.5 degrees no matter which one you look at. Again, if you turn it upside down, it's going to look the same, no matter how you turn it. With trigonal bipyramidal, these three form a flat triangle. And then this one, and by the way, that flat triangle is 120 degree angles within that plane. So this one to that one's 120, this one to that one's 120, this to that is 120. The one up here is different though. It's 90 degrees from all three of those. And the one down here, same thing. It's 90 degrees from all three of those. So they're different. And that's going to matter to the atoms. Like if you have to put a lone pair on there, where do you put it? Do you put it in one of these 90 degree locations or one of the 120 degree locations? Okay, just some terminology here. We kind of treat it like this triangle is the equator of the Earth. So that's those we call equatorial positions. And then these two poking through it are the axis or the axial positions. So you could talk about an atom being on an equatorial position, which makes it 120 degrees from the other three around it. Or you could make it an axial position, 90 degrees from the equatorial ones. Okay? Now, it turns out the ones on the equatorial positions have less overall repulsion. Why? Because they're 120 degrees from some of their neighbors, further apart. The ones in the axial positions, they're 90 degrees from all their neighbors. So they're packed in closer to their neighbors, which means something at an atom or an electron pair in an axial position will experience greater repulsion than an electron pair in an equatorial position. So, turning that around, if I have an electron pair that is highly repulsive, maybe it's got a really intense charge density like a double bond. Maybe it has a highly electronegative element or some such. There's a lot of electron density there. It's going to tend to go on an equatorial position rather than axial. The axial positions get the ones that don't repel as much. Okay, so that's important to realize. And by the way, I'll point out now, since we're on the topic, lone pairs are more repulsive than bonding pairs. Okay? Why is that true? Because bonding pairs are constrained between the two nuclei. So the electron clouds are kind of pulled together really tiny. Lone pairs are not constrained. So they expand up and become really big giant balloons, which makes them push more on the balloons around them. Or in other words, lone pairs are more repulsive. So if you have a molecule that has a lone pair on it, if you're talking up here with trigonal planar, doesn't really matter where you put it. They're all equal positions. Same with tetrahedral. Doesn't matter who the lone pair is. They're all equal. But with trigonal bipyramidal, it matters. So if you have a lone pair, you're going to put the lone pair on an equatorial position, one of these three, not on an axial position. If you have two lone pairs, both of them go equatorial, and so on. Okay, so that's important to realize. It's going to matter for the shape of the molecule where you put it. Now, the last one, octahedral, if you have 6 pairs of electrons. In that case, again, it's called an octahedral shape, and it is symmetric. I guess you could think of it as a square bipyramid, but it's completely equilateral. Bond angles inside the square are 90 degrees. Bond angles above and below the square are 90 degrees. So once again, it doesn't matter how you turn it, it's going to look the same. And therefore, there's no worry about axial or equatorial positions. If you have a lone pair, put it wherever you feel like. It's all equivalent. If I put it over here, I could turn the molecule on its side, and now it's down here, and the molecule is the same molecule. Okay? So there's that. Now, the next several slides are looking at, maybe I'll do this as a slideshow now, are looking at the different shapes you can get beyond this just overall geometry. So, if you have 2 pairs, okay, the electrons are arranged linearly. Now, here we have none of them are lone pairs. In other words, both pairs are being used to make bonds. In AX notation, AX2E0. They don't show the E's here. Okay? That's linear, obviously. There's the central atom. There's the 2 attached atoms on the bonds. Bond angle's 180. Beryllium chloride is an example of that. Now, what if you have a lone pair in there? They don't show it on this chart. You have 2 pairs, but one of them, let's say this one's a lone pair. What happens then? Well, it's irrelevant because now there's only one bond. There's no other bond to have an angle with. Yeah, there's a lone pair over here now, but you can't see electrons. You can't detect lone pairs. And so presumably the lone pair is arranged linearly on the other side of the molecule, but who knows? So in the case where there's 2 pairs, but one of them's a lone pair, in other words, AX1E1, if you want to use AX notation, it's a trivial situation where there's no bond angle at all because there's nothing to have an angle with. So we ignore it on these little diagrams. Now, let's go on to 3 pairs. If you have 3 pairs, they're arranged trigonal planar, so which we looked at just before. The simplest case, of course, is they're all used. There's 0 lone pairs. Or, again, to use AX notation, is AX3E0. All right, great. So there's your trigonal planar. As we expected, bond angles are 120. And they give you example molecules that do that. Now, what if you have 3 pairs, which, again, they're arranged trigonal planar, but one of them is a lone pair? Okay? So, in other words, AX2E1. So notice, looking back at my trigonal planar, one of these 3, let's choose this one, is going to be a lone pair. So now the molecule looks like this down here. AX2, there's the empty or lone pair, E1. Now, again, remember, you can't see lone pairs. You can only detect where the atoms are, the nuclei. So what you're going to see is chemical X, chemical A, chemical X bonded at an angle to each other. So the molecule is angular shape, or some books call it a bent shape. Means the same thing. Okay? The bond angle in there is still 120 degrees. The sulfur dioxide molecule does this. You might want to do some Lewis structure for these and verify to yourself they have the 2, 3, whatever pairs we say they're having. And they have the lone pairs and all. But I'll give you some examples to try for homework anyway. So notice, you can get a molecule that's trigonal planar when you use all the lone pairs to do bonds, you can also get a molecule that's bent at an angle when you have 3 pairs, but one of them's a lone pair. So here you have 2 atoms attached to the center atom and it ends up linear. Down here you have 2 atoms attached to the center, but it ends up bent at an angle. Why? Because you got a lone pair pushing them together. If that lone pair weren't there, this chemical X would push up and away and you'd get back to linear 2 pairs. But with 3 pairs, that lone pair is there and it's affecting the shape. So in a sense, we can't see the lone pairs, but we know they're there because they're pushing the X's to a 120-degree bond angle. Now, one last thing to say about this. These bond angles we're talking here are theoretical angles. In reality, they differ from that slightly. But the reasons often are understandable. Remember on the previous slide I said lone pairs are more repulsive than bonding pairs. Okay? So this lone pair up here, yes, we're saying 120, 120, 120 for the bond angles. But this lone pair up here is actually more repulsive than these bonding pairs. And so these 2 X's, their bonds get pushed a little closer together. So the actual bond angle, if you were to really go measure sulfur dioxide, the actual real bond angle is probably closer to 119, 118, a little slightly bit less than 120 because of the additional repulsion of that lone pair. Now, for our purposes here, we're going to give theoretical angles. So if I ask you, what's the bond angle of sulfur dioxide? You would go through your Lewis structure. You would then use VSEPR to figure, oh, it's an angular molecule. And you would say, okay, it's a 120-degree angle. Yes, we all know it's slightly less than that, but whatever. Now, continuing on, a trivial case, what if you have 2 lone pairs? Well then, if both these are lone pairs, you have nothing to form an angle with again. And so we don't have to worry about that. Now, let's quickly, with my last 3 minutes, look at 3 pairs. And then we'll do the expanded ones tomorrow. 4 pairs gives you a tetrahedron overall geometry. Simplest case, there's no lone pairs, AX4E0. We bond all the pairs. That gives us a tetrahedral overall molecule, 109.5 degree angle. Methane molecule does that. Here it is. Now, what if instead I still have 4 pairs, so they're still arranged tetrahedrally overall, but what if one of them is a lone pair? Okay, to use AX notation, AX3E1. So let's make the top one a lone pair. We could make any one, it wouldn't really matter, but just for convenience, we'll make the top one a lone pair. So now it looks like this, and you'll notice what we have is a squished pyramid. The base of the pyramid is a triangle. The pyramids in Egypt are squares, right? But this is a triangle pyramid or a trigonal pyramid. And then, now, a tetrahedron was a trigonal pyramid too, but notice the central atom was in the middle of the pyramid, right where the pharaoh is, right? And then you had another chemical X bonded above it, making the whole thing symmetric. With this, we instead of putting a chemical X up there, we put a lone pair up there. And now the pyramid becomes squished, and the dead pharaoh is sitting on top of his pyramid now. Okay? So it's a squished, flattened pyramid, no longer symmetric, so you can't call it a tetrahedron. So we just call it trigonal pyramidal shape. Okay? Bond angle still 109.5, yes, slightly under that, maybe 108 or something like that, but similar. The ammonia molecule does that. Here it is what it looks like without the lone pair to distract you. Okay? One more molecule we'll look at today, and that's if you can ignore this one down here for today. If you still have 4 pairs, so it's overall tetrahedral, but you have 2 lone pairs now. So AX2E2. Now here's your overall tetrahedron, but we made the top one a lone pair and we made the left one a lone pair. So now the 2 chemical X's are attached at an angle again, so the molecule is once again an angular molecule. How is it different from the previous angular we looked at? Before, the bond angle was 120 in that one, because there's only 3 pairs. Here there's 4 pairs, so the bond angle is still 109.5. Again, slightly less because of the extra repulsion. An example of that is the water molecule. They wrote it backwards here, OH2, but whatever. The water molecule is exactly in that situation. The oxygen has 2 lone pairs on it, so you end up with this 109.5 degree angle. Again, it's pushed together a little more, so you get 104.8 degrees as the actual bond angle of water. The true angles deviate slightly from ideal. So let's stop there. I'm almost out of time. I'll give you some work to do on these. Tomorrow we'll look at the expanded octets and what their shapes end up being. All right, we'll see you tomorrow.